Hi guys, so just continuing from the previous lecture, the set of examples we were looking into the compounds which are either enantiomers, diastereomers, or identical or others, right? So let's look at the fourth example wherein we have three cyclohexene rings. Okay, so in the cyclohexane rings we have substituted this, 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 and 2-methyl here. Okay, so let us name them 10, 11, and 12. So which two are enantiomers? Um, these two are certainly not enantiomers, and this is obviously 12th is out of the picture because it is existing as chair form. So 10th and 11th are diastereomers, and obviously 10, 12, and 11, 12 are positional isomers. Okay, why they are positional isomers? Because the position of the methyl dimethyl is changing. It was previously on 1 and 3, now it is on 1, 2, 3, 4, 1, and 4. Okay, let us look into another example where we have another two cyclohexane rings. We draw two cyclohexane rings, and on it substituted is O. Br is coming out of the plane. Similarly, O and Br is coming out of the plane. Sorry, Br is going inside the plane, and H is coming outside the plane, and in this case H was going inside the plane. Okay, so what are these two compounds then? So if you carefully see, let's first mark them as 13 and 14. So if you carefully see that if you rotate this across this plane, if you rotate this cyclohexane across this plane, you will see that Br will come, which was uh, away from the plane and lower away from the plane after rotation of 180 degree. In this way it would be uh, into my face and above, right? And it would look something like this. When we rotate it 180 degree, it will look something like this: Br here and H here. Okay, so 13 and 14 becomes the mirror image of each other, or they are enantiomers. 13 and 14 are enantiomers. Okay, let us look at another example wherein we have, is this aniline? No, aniline requires 4 double bonds. Okay, second we have this form of the same compound. Okay, and here we have the double bond between this carbon atom and this carbon atom. Okay, so let us name these compounds as 15 and 16. So 15 and 16 are obviously not enantiomers, they are obviously diastereomers. It is showing geometrical isomerism, how these two hydrogen atoms were cis to each other, now they are trans to each other, hence they are diastereomers. Let us look at another example. Here we have H, Br here, CS3 here, 1 CS3 here, H and Cl here, and BrH here, and ClH and CS3 here. Okay, so let us name them as 17 and 18. Okay, so for comparing them, let us rotate uh, this bond anti-clockwise 180 degree, and this bond clockwise 180 degree. Okay, so what do we get? We will get something like, we will get HBr CS3, and we will get ClH CS3. Here we will get here we will get HBr CS3, and here we will get, this is the same. Okay, so now let us compare between them 17 and 18. So as you can see that 17 and 18 will be diastereomers of each other. How? Because if you rotate the second or the 18 compound in the same plane but 180 degree, so this was the plane of this compound. So in the same plane, if you rotate it perpendicular to the about the perpendicular plane 180 degree, so you will get something like this. The H would go in the left hand side, CL here, CS3 here, and Br would also go to the left hand side, H here and CS3 here. Okay, so now you can see that they are not mirror images of each other, so hence they are enantiomers. So 17 and 18 are enantiomers. Okay, or I think I might have misjudged this example, and actually they are identical. I just noticed it now that Br is here, Br the same here, Cl is here, Cl is same here. No, they are identical. I beg your pardon, no need to do the rotation, but obviously you can see this as an example of rotation. How do you make a compound after rotation? But these are two identicals, no need to rotate it. Okay, so now let's have a look at this. When we have our eighth example, we have something like, in Newman projection we have DH and CS3 here, and on the back carbon we have CS3, Cl and Br here. Okay, and here we have H, D and CS3, and on the back carbon we have Br, Cl and H. Okay, so actually this is just a H here, this is not CS3, this is just an H here. Okay, so if you draw the Fisher projection of this compound, you will get something like, oh, let me name them as 19 and 20 first. This is 19 and this is 20. So if you draw the Fisher projection of the same, you will get something like, for the 19 you will get HD and CS3 here, and you will get HCl and Br here. Okay, for the 20 you will get H, D and CS3 here, and on the back carbon you will get Br, H and, oh sorry, did I draw it right? Yeah, so Br, Cl and H here. Okay. Oh, sorry, I forgot to rotate this bond. You have to rotate it in YY so as to form the fissure. So first, from the Newman, you have to form fissure of the form YY, and from the fissure you have to make from the sawhorse, from the Newman you have to make sawhorse. From sawhorse you make new fissure, and from the sawhorse to make into a fissure you need to have YY. So actually I have drawn it wrongly. It should be, when you rotate it, H would come to the down hand side, CL will come right, VR will come left, and similarly VR will come to the downside, H will come to the left, and CL will come to the right. Okay, so from here you can actually make the R and S. So this would be R, this is S, this is S, this is S. Hence 90 and 20 are diastereomers. Okay, let us look at this example wherein we have so I will leave this question as a homework for you, just writing the question here. CS3 here, CS3 here, you will have CS3 H BR H CS3 and CL. So this is compound 21 and 22. So you have to tell me what is the relationship between 21 and 22. So the answer would be they are diastereomers. 21 and 22. Okay, just make them into YY, make the then fissure, make RS, then compare. Okay, so in the next lecture we are going to see some more of the examples before jumping into the definitions of chiral compounds, the chiral compound, optically active, optically inactive compounds. So till then, good luck and goodbye.